All right, good evening and welcome to lecture 25 for MT225. Tonight is our last formal lecture, I suppose. Monday night next week is just open for review, student-driven review. So if you have any questions, bring them in. Otherwise, I might just give some tips and tricks like I did for the second exam and leave it at that. But if you've got problems that you want to see worked out, Monday night would be a good place to bring them in. Tonight we're going to finish up our last section, which is to take a look at the bending and deflection of beams. So we'll see what happens when we load up a beam and see if it see how much it deflects by, and see how we can model that. So let's see. Homework 9 is due this evening, and it looks like people got the message on that I had the wrong due date on the original printout of the assignment. So tonight, 4/28, we do have homework number 10, which I just posted. So if you looked for it a little bit earlier, I neglected to post it yesterday. I meant to, but must have gotten distracted and didn't get it up on there. But it's on the website now. So it's so it is that is due on our last on our exam 3 date, which is on May 5th. That is a bonus because it is due when the exam is due, but I strongly encourage you to take a look at it. It will give you good practice for the exam. So if you can handle that homework assignment, chances are you can handle the exam with no problem. And exam 3 will be next Wednesday night. So next Wednesday night at this time, we should be well into our exam. And a reminder, you can have index cards for that. Since it's a third exam, you get 3 of them. Probably won't need them, but 4-inch by 6-inch cards, and food will be provided. And then 1 week later, we have our final exam. The final exam is comprehensive. It covers everything from the beginning. It's probably in the neighborhood of 9 to 10 problems, depending on how I set it up, but covers everything from the basic math and solving equations we did at the beginning, equilibrium problems, trusses, and strength of materials. So everything from the beginning to tonight's class. So, and I have posted a sample exam 3. I think I posted one from way back in 2016. So, good representative exam for what exam 3 would look like. So I'd encourage you to take a look at that. Solutions for that are also there. And I will be posting sometime next week a sample final exam. So before we get too far, let's take any homework questions. I've had one come in here for problem numbers 5D and 5E. So let's take a look at those first. Any earlier than that? Anything in 4 or before? All right, so let's take a look at problem 5. Let me load that up. And let's see, homework 9. Oops. There we are. There's Zoom share. All right, so there's homework number 9. We're down here in problem number 5. So problem number 5, here we've got 2 10-inch by 6-inch plates that are joined together along the 6-inch dimension and subjected to a load of 10 kips. So that's 10,000 pounds. This is the typical lap joint kind of problem. And this is a shear stress problem. The fundamental thing to keep in mind with shear stress is the basic definition. So shear stress is the applied force divided by the area that is resisting that shearing force. So I like to think of it as the area that'll break through if the force is high enough to get over the shear strength of the material. So what we've got are these plates, and we've got a lap joint, and they give us some dimensions to that, but I'll just sketch a sort of generic lap joint. So what we call a single lap joint is there. And let's see, there's the homework. we've got 10-inch by 6-inch plates joined together along the 6-inch dimension. So if I were to do a top view on this, I'd have the 6-inch dimension going top to bottom of the page. Let's sketch that out actually, so it's a little clearer. So we have the two 10-inch by 6-inch plates. So I'll do a little sketch here before I go back to the display. And I picked 6 inches. That might seem familiar because of the FAA. A lot of the FAA questions involve 6-inch lap joints for some reason. So I'm used to that from our sheet metal class. So the width of the joint is 6 inches, and the length of the plates 10 inches. And let me do a front view here. So we want for specifically what was asked for were D and E, which are the I think it was D and E. Yeah, D and E, which are the weld questions. So I'll look at those here. It's a 3/8 inch bead, and it's whether or not it's welded on both sides or just one side. So let's go back to the display. So here's the picture. So we've got these 10-inch by 6-inch plates, and the it's joined along the 6 inches, the 6-inch dimension, overlaps by 1.6 inches. That's not really useful for parts D and E, but it is for part A. Part A is about the only one you should use that 1.6 dimension in. Now, what we're looking at is a welded joint for this one. And so you'd have to make some reasonable assumptions here about that welded joint. Specifically, it says it's a 3/8 inch bead. So what I'd be thinking of here, and I'm going to try and draw it in a different color, is a little 3/8 inch bead of welded material right there. Now, in reality, you're going to have some undercutting, or you're going to weld into the base metal, and you'll actually have a little bit more area covered here. But just for a simple calculation, we can say this is a 3/8 inch wide weld. So that's a single bead. So the area that's actually resisting shear, when we apply a force of, in this case, 10 kips in both directions, that means that to keep this thing from separating, the 10 kips force that's pulling to the left here has to be pulling on the weld with 10 kips of force. So that 10 kips of force is spread out over 3/8 of an inch in this direction, and then over the whole 6 inches in the other direction here. So the bead goes the entire way through. And this is actually not that far off on how we do strength analysis of welds. It's made more complex when you're trying to figure out what the failure point is going to be, because you have to know what the properties are of that welded material and that welded joint. With certain sticks, for example, if you're doing arc welding, they actually tell you what the tensile strength of the welded material is going to be after you weld it. It's in those 4-digit codes for the arc welding stick, for the welding rod. So we've got this 3/8 inch wide by 6 inch long area that the 10 kips has to be spread over. So that's the area that is resisting the applied load. That's the area that will break if it was too strong of a load. So this would be D, where we just have one bead. So the area that's resisting the stress is 3/8 of an inch by 6 inches. And if we multiply that out, let's see here, 0.375, 3/8 of an inch times 6, that's 2 1/4 square inches. So 2.25 square inches. So our shear stress is the force spread out over the area that's resisting that force, That's 10 kips of force over 2¼ square inches. And that gives us a shear stress of 4.444 kips per square inch, or KSI. So that's the shear stress involved, and that's as far as we have to go in this problem for figuring out the shear stress. If this was a problem more like what we'd see for homework 10, which is out now, is we'd be asking, well, is that too much? What is the strength of that joint? Or using a particular material that can handle a certain amount of KSI, how much force can we put on it before it breaks? But here we're just calculating the shear stress. Now, part E asks, well, what if it's welded on both ends? So you weld one joint, you do what we call a, well, you could call it a double lap joint, but that refers to something else. We'd have another bead over here. So we'd have another bead, and I'll draw it with a hidden line right there, like that. So also 3/8 of an inch by 6 inches. So this contributes another area of 2.25 square inches. So we're doubling the area that we're spreading our force out over. That's going to cut the shear stress in half. If we keep the force the same, but we double the area, we get half the shear stress. So our shear stress for part E, the shear stress would be the same 10 kips of force, but now it's spread out over 4.5 square inches, 2.25 times 2, and that'll give us 2.222 kips per square inch. Make sense on that one?
Yep. Yeah, I had it right. I just wasn't sure if we could account for, like one stuff.
Yeah, I mean, it can get a lot more complex to try to make it real, but or at least as close to real as possible. But this is 90% there. Everything else is just really fine detail and figuring out, because you're going to get some. It's not going to be a straight line here. If you've welded, and I think everyone in the class has done welding, you're going to end up with eroding some of the base material. You're going to kind of go in. You got to have some penetration there, and that's going to be an area. So a lot of times we just have some rough estimates for what the area is. This is mostly there. This is pretty close to it. Any other homework questions? All right, so let's get into the content here for tonight. So tonight we're going to take a look at bending and deflection of beams. Now we've looked at beams before. We looked at simply supported beams, where we had two supports, one on each end, and we put some load on it and found the reaction. So it's kind of our introduction to truss problems, because it was the first step in solving the truss problem. Well, tonight we're going to look at it from a little bit of a different perspective. In the problems that we solved in the past, we had a supported beam, we found the reactions, and those reactions are correct, but it never brought in what happens to the beam. Now that we know things about strengths of materials and how materials react to forces, we should expect a reaction from the beam itself. The beam should change shape. And what beams do when we load them is they bend. And so first we have to take a look at what bending is, and then we'll look at how we can model how much bending or how much deflection is going to take place. And this is something that if you deal with construction, even something as generally simple as residential construction, you run into these things all the time. It's what tells you whether you're allowed to use a 2x6 or a 2x8 to span a certain, to use as a floor joist or use as a ceiling joist. It's where a lot of the tables come from in residential code. So it's an important kind of idea. We're going to take a look at just two basic simple cases, and they're really the ones that are the most practical out there. Every other situation, you can look up the appropriate information to alter the calculations we do for different for those kinds of situations. So if you work with I-beams, for example, you can modify this to apply to I-beams pretty easily. So let's take a look at bending in beams. So beams are pretty common structural elements. We use them all the time. How a beam behaves under load depends on first how it's supported. Essentially, consider something like a floor joist where it's supported at the ends and it's free in the middle, or something like a diving board where the supports are toward one end and the other end is free. And we've talked about supports before, roller supports and pin supports and all of that. And those come back a little bit here. The types of supports we use classify the way the beam is treated. So we have the simply supported beam or the simple beam. That's what we've worked with mostly. And a lot of our example problems were rollers and pins on the ends. So we supported on both ends by these nice simple supports. The fixed beam is a little bit of a different story, and we're actually not going to look at the fixed beam for the most part. Fixed beam, you could imagine you take both ends of the beam and you stick it into wet concrete. So you have a wall, for example, and you stick one end of the beam into the wall, let the concrete dry around it, and then you build another wall around the other beam and let the concrete dry around that. That beam's not going anywhere. That's what a fixed support is. Remember that rollers were able to roll a little bit, pins could hinge, they could pivot, but fixed beams and fixed supports can't go anywhere. A little bit more important to us, and something we will look at a little more closely, is what we call the cantilevered beam or the cantilever beam. In that case, you just have a fixed support on one end. So you've got a wall made out of wet concrete, and you shove one end of a beam into it and wait for the concrete to dry. One end stuck, can't go anywhere. The other end's completely free. It's sort of the idealized diving board kind of setup. And then sort of the real diving board is what we call an overhanging beam, where you have basically a simple beam, but one of the supports is further in than the end. And I've got some pictures for each of these on the next slide. The top one is a simply supported beam, should look very familiar and be something we're pretty comfortable with. The last one is the overhanging beam. The overhanging beam is very similar to the simple beam. The analysis is very similar. It's just not as easy to figure out as far as bending goes. So we will instead look specifically at the cantilevered beam, since the cantilevered beam basically behaves the same as everything on the overhanging beam that is away from the last support. So if we just look at how things are behaving from that last support, we get a pretty good approximation from the cantilevered beam. So cantilevered and simple are kind of the two extremes, and we're going to look at those specifically. Everything else is kind of close, or at least less dramatic than those two. So if we know how to handle simple and cantilevered beams, we know how to handle everything there is. Now, let me say a thing or two about shear and forces in bending. When something bends, let's go over to the display here and we'll see what happens when something bends. When something bends, we apply a torque to it. Essentially, if I wanted to bend this beam so the ends of the beam were going to go down, I might grab hold of it and twist it like this. I'd push my thumbs up while my fingers are pushing down, and that would give me a torque on each end, or a moment on each end, that would make it look like that. And that would cause the beam, if the beam were extremely flexible, it would cause the beam to look, in an extreme case, something like that. Now there is something that we've learned about bending, and something you might remember if you remember back to sheet metal. When you do a bend, you have different stresses in different areas. The outside of the bend has to get longer, so it's put into tension. The inside of the beam has to get smaller, so it's put into compression. Somewhere in the middle, that switches. We have compression on the outside, tension, or we have tension on the outside, we have compression on the inside. Somewhere we don't have any stress at all. And in sheet metal, we called that the neutral axis, and that's because sheet metal borrowed that from structural engineering. So we've got some line here going in this third dimension out of the page that is our neutral axis. And if we were to zoom in on that area, what we'd see is we would see tension on the top, and that tension gets lower and lower until there's nothing at the center. And then we'd see the direction switch. We'd see compression on the other side. That's what the state of stress is looking like inside the beam. Part of the beam is in tension, part of the beam is in compression. At the neutral axis is where it switches. So what we say is bending is a combination of tension and compression. So combination is a mix. So we can't say something's truly in tension or truly in compression when it's bending. That was why, for example, we couldn't say whether a frame member was in tension or compression, because frame members, if we loaded it in the middle, that would be bending. And bending is a mix of tension and compression. So it looks something like this. Now, if we're worried about failure, and we're not really going to look too much at failure of beams here, but if we're worried about failure, we're worried about this area right here. We're worried about the tension area, just like we would be in a wing. In a wing that's lifting, the bottom of the wing is in tension. That's where we're going to be looking for cracks. Tension causes cracks. Compression doesn't. Compression squeezes cracks together. So we are most worried if we're worried about where this thing's going to fail and how much strength it's going to take before it fails, how much load it's got. We're looking at the outer edge of what's in tension. So that's what it kind of looks like inside. Now, if we put all that together, we can figure out how the beam is going to change shape, because we know something about what happens with tension and elongation, stress and strain. We know something about how that fits together. We know something about how compression creates a stress that causes a shrinkage of the material, a stress and a strain. If we put all the math together on it, we can actually calculate from the material that the beam is made out of and some information about its geometry, we can figure out how much it's going to deflect. And fortunately, some very smart people have gone through and done that analysis and come up with nice, simple equations that we can use for nice, simple situations. Reality is always going to be more complex, and we can use a computer in that case to model it. But for simple cases, if we know enough about the geometry of the beam and what it's made of, the material and the shape, we can figure out how much it's going to move and be pretty accurate about it. And that's what we're going to take a look at here. So let's look at deflection of beams. So deflection of beams is pretty simple because there are only a few cases that we can actually write down. The rest of them require computer programs to work out. When we place a load on the structure, we generate internal stresses. That's not new. That's something we've been working with the last couple of weeks. We load up a structure, we create stresses in response. The material generates a stress in response to the external load. The structure then responds to that stress by changing shape, by straining, by elongating or compressing. Well, if we have a mixture of elongation and compression, that's bending. So we've seen the relationship between stress and strain for tension, for compression, for shear, and something that you should recall is going to be a factor there is the Young's modulus. Young's modulus tells us about the relationship between stress and strain, the modulus of elasticity. That's all about the material. Once we know about stress and strain, we can use the geometry to turn that into real forces and real changes in shape, lengths. So today we'll see how beams change shape in response to those bending stresses. So two factors that we absolutely need to have in order to determine how a beam is going to resist bending or how much change in shape we'll experience is first the material. The modulus I went over last time, the modulus describes how stiff the material is. Essentially, it's a resistance to stress. The bigger the modulus is, the less strain you get for every applied unit of stress. So the bigger the modulus, the less the more stiff the material is, the less it'll change shape. Now that tells us about the material. That's all about what it's made of. Is it aluminum? Is it steel? Is it heat treated? Is it cast iron? Then there's got to be something about shape. And this is a new idea. This is something you may not have experienced before. So we'll slow it down a little bit here. What really resists bending in a beam is the cross section. It influences how much the beam deflects. We have a measurement of the resistance to bending that a shape gives. So independent of material, doesn't have anything to do with material. There is a resistance just due to the shape. And we call that resistance moment of inertia. Kind of a strange name. It dates back to the math that's involved in actually calculating the moment of inertia. You may recognize at least one word in there, moment, and it has to do with multiplying by a position, which is exactly what we do when we find moments in, say, weight and balance. We multiply a force times an arm. It's the same kind of calculation here. In fact, it's pretty similar. But what the moment of inertia does physically is it tells us how resistive a shape is to bending. And let me illustrate that idea here. So let's take something like a 2x4. Now, if you take a 2x4 and you lay that 2x4 on its side and you put it on some supports, I think everyone have the experience of laying out something like this and stepping on the middle of it and feeling it flex quite a bit. 2x4, if you got an 8-foot long 2x4 and you set it down on a couple supports and you push down in the middle, you know it's going to bend pretty easily. If you look at the cross section of this, if we were to take a little cross section through here, that cross section would look like this. It would be 3.5 inches by 1.5 inches if it's typical dressed lumber. Well, that shape doesn't resist bending very well. And the reason it doesn't resist bending very well is because if I draw the neutral axis in, the neutral axis is a horizontal line going through the middle. There's not much material above or below that line. Resistance to bending is really about how much material is distributed far away from the neutral axis. And I think everyone's probably had the experience, or at least has the intuition, that says that if you rotated this 2x4 so that the long dimension, the 4-inch dimension, was upward instead of laying on its side, that you'd have something that would be a lot stiffer, that would be harder to, so if you push down here, it's not going to deflect as much. Now the cross section here, if I draw my cross section through, it's the same area. But if I draw the neutral axis, which is a line right through the middle, there's much more material. There's much more area distributed farther away from that neutral axis. That gives us an indication of resistance to bending. The greater the area is away from the neutral axis, and the farther that area is away, the stiffer the material, the stiffer the area is with respect to bending. That's what we call the moment of inertia. The moment of inertia up here would be low. So this would be a low moment of inertia. This would be a high moment of inertia. Now, if you had a 2x4 and you were getting too much flex out of that, maybe you go to a 2x6 or a 2x8, a 2x10, 2x12. The more, what that's doing is it's making this dimension bigger and bigger so that we have higher and higher moments of inertia. If that doesn't give you enough resistance to bending, maybe you go to something like an I-beam. An I-beam, if we look at how an I-beam is put together, something kind of interesting pops out here, that if we look at the neutral axis, the I-beam is set up so that it has a large amount of area distributed far away from the neutral axis. This would give us a very high moment of inertia. And that's why we use things like I-beams to span pretty significant distances. They are that shape, independent of what it's made of. Even if we built this out of wood, if we built this out of any material, it would have the same moment of inertia. Moment of inertia is just about the geometry and how far the area is spread out around that neutral axis. Now, for I-beams and things like that, we can go and look up what the moment of inertia is. There are tables out there for that. For material that's got a rectangular cross section, there's an equation. And that equation tells us what the moment of inertia is. And I'm not going to derive the equation. That is more of an exercise for kind of it's typically done in a calculus class. So if you go on and take calculus, chances are you'll learn how to calculate moments of inertia. But if I have a rectangle with dimensions, and these are the typical dimensions that are used, we call the vertical dimension typically H, the horizontal one B, and the moment of inertia is BH cubed over 12. So you're just going to have to take that equation on faith, and that's in the notes. We'll see it here in a little bit. But notice notice a couple things. First off, H, the vertical dimension, and the one that resists deflection the most, the one that makes the moment of inertia higher, that's cubed. So it doesn't take very much extra height to get a lot more stiffness and resistance to bending. The B dimension, the width, doesn't really do much. So if I take two 2x4s and I nail them together, I'm going to get twice the moment of inertia. I'm not going to get much more than that. But if I go and take a 2x6 or 2x8 or 2x10 and put it in here, that H is going up, so I'm going to get a much bigger moment of inertia. The second thing to notice is the units. The units are weird here. If B is inches and H is inches, we have inches to the fourth. It's weird, but that's the unit that's associated with moment of inertia, inches to the fourth. So let's see how that plays out here. So the moment of inertia is about the shape, and the bigger the moment of inertia, the more resistance there is to bending. So moment of inertia depends on just the cross-sectional shape. For a rectangular cross-section, the moment of inertia, which the symbol I've written here on the paper, MOI, a lot of times they just reduce it to I. So I is the symbol for moment of inertia. Think I-beam or inertia, BH cubed over 12. So here's the picture. There's our neutral axis. H is the height measured top to bottom, not from the neutral axis. So that would be the 4-inch dimension in a 2x4. B is the width. So that would be the 2 inches or the 1.5 inches. So BH cubed over 12. So let's find out what the moment of inertia is here for a typical 2x4 set up in this configuration. So we'd have 1.5 inches there, 3.5 inches there. So the moment of inertia would be BH cubed over 12. If I've got B is 1.5 inches and H is 3.5, I'd cube the 3.5, multiply it by 1.5, and divide it by 12. So we have 1.5, 3.5 cubed. So you might have to look for a while to find your cubed button. You don't use that too often. And then divide it by 12. So it looks like I'm getting 5.3594. and the units would be inches to the fourth. Now let's see what the difference would be if I went to a 2x6. Now 2x6 is 5.5 inches tall instead of 3.5. So for a 2x6, the moment of inertia would be 1.5, same thickness, but 5.5 cubed over 12. And because of that cubed, we can expect a pretty dramatic effect here. 5.5 cubed times 1.5, all divided by 12, we get 20.797 inches to the fourth. We basically get more than almost 4 times more moment of inertia. That's the effect of that cube. So even though we only made the thing 2 inches taller, it added a lot more moment of inertia. So that height dimension is very, very important. So the neutral axis, that's our line about which bending happens. So, and that cube dimension is always perpendicular to the neutral axis because moment of inertia and resistance to bending depends on how much area is distributed far away from the neutral axis. So it's always biggest for shapes that have lots of area far away from the neutral axis, like an I-beam. Now, how this all wraps together into the deflection of a beam. We're only going to look at 2 cases for deflection. One is just a simply supported beam that we load in the simplest way possible, dead center. And this is actually what's used in building code when looking at floor joist spans. When you have to pick a floor joist size to use, and you've got a certain span, say 12 feet, you have to cover. The size, the tables they have in the building code are based on having no more than a certain amount of deflection if all the weight is concentrated at the center. So it's the worst case scenario loading for that beam is to put load at the center. Now the other extreme we're going to look at is the cantilevered beam. So a beam that is set in concrete on one end, but is free on the other. And the worst case scenario for bending, the thing that's going to make that beam bend the most is to put the load all the way at the free end. So we'd load it at its end. So only 2 cases because those are the ones that have the simplest equations. You can certainly go and look up other cases out there, and there are whole tables and whole books full of different cases out there. But there's the picture for the simply supported beam. So we've got some load dead middle of this length L, and we want to find out how much it's going to deflect. And what this gives us is the maximum deflection. It gives us how far the very middle of this beam will deflect. Areas toward the supports, they're not going to deflect as much. So that's our setup. Now, in order to solve this, we need several pieces of information. First, we need how much load is applied. We also need what material the beam is made out of. That'll tell us the Young's modulus, which will tell us about how the stresses and strains relate. If this is a stiff material or a material that changes shape a lot. We need the cross-sectional area because that tells us the moment of inertia. Or we need the moment of inertia told directly to us. We either need the dimensions or so we can calculate the moment of inertia, or they need to tell us the moment of inertia. And then we need the length of the beam because length is how we turn strain into distance. So we need some amount of information about distance. So we need the modulus for the material. That's the letter E, which we can look up. We need the moment of inertia for the cross section of the beam, which we'd either calculate from BH cubed over 12, knowing B and H, or we're told what that is, or we look it up in a table. There's the equation. So a little bit of a complex equation, but let's write it down and give an example. So the max deflection, we'll just call that D, is the force. So it should make sense that you get more deflection for more force, and those two are proportional. You push twice as hard, you get twice the deflection. The length is cubed. So that means that the deflection's really sensitive to length. If I increase the length just a little bit, I can potentially get a lot more deflection. So I might have a beam that's okay for 4 feet of span, but if I try to go to 6 feet, it's way too much deflection. Just a small increase in length can make this thing much more flexible and much more, make it deflect much more. Then there's the number 48, which is more about the details of the geometry and the loading. We've got dividing this, the modulus. So the stiffer the beam is, the less deflection we'd have. That's our resistance to the material bending. That's the how much stress relates to strain. And then we've got our modulus, or we've got our moment of inertia. We've got the shape's resistance to bending. So those all show up in the denominator. So the higher the moment of inertia and the more stiff the material is, the higher the modulus, the less deflection we'll get. So we've got two competing groups of information. We've got force and length trying to drive the deflection up, and we've got the material's modulus and the moment of inertia trying to drive the deflection down. So there's the equation. The deflection is, the max deflection is 4 times the length cubed divided by 48 EI. So let's try it here for our let's say a 2x4. So let's put 100 pounds on the middle of that 2x4, and we will make the length of the 2x4. Let's make it 6 feet. Now the moment of inertia we've already calculated. For a 2x4, it's 5.3594 inches to the fourth. Now the only other thing we need is the material's stiffness, the modulus. And for that, we'd have to go to a table. And I've got a reference table here for different materials. And there are properties, design values for typical timber construction. And so I'll assume this is typical southern pine, which is referenced quite a bit in building codes. Southern pine has a modulus of elasticity of 1700 KSI. 1700 KSI. Now, the big deal here with working on these problems is we have to make sure the units all work out correctly. We are looking for deflection in inches. The forces have to be consistent, and there's a force unit coming in with force. There's also a force unit coming in with the modulus through kips, kilopounds. Then we have to make sure the lengths work out. That we have inches and possibly feet here. So we've got to be careful. In order to make this work out, we've got to make sure absolutely the force units are consistent. So if we have forces in pounds, our modulus has to be in PSI. If we want to use the modulus in KSI, we'd have to put our load in kips. So this would be 1/10 of a kip, 0.1 kips. As long as they're consistent. So we could either use a modulus of 1,700,000 PSI and 100 pounds, or we can use 0.1 kips and 1700 KSI. If you mess that up, you end up with your answer being a factor of 1,000 off, one way or another. It's either a factor of 1,000 too big or a factor of 1,000 too small. So you really want to be careful about that. The length units we really don't have to worry too much about as long as they're consistent. Those we don't get a lot of choice in because typically our moments of inertia are in inches to the fourth. And for everything to cancel out properly, we need to have our lengths in inches too. So be careful if you're given a length in feet, you're going to have to turn that into inches. Since our modulus is an inch, or since our modulus involves square inches and our moment of inertia involves inches to the fourth, that way we'll always get inches out for deflection. And converting the units over to feet would be a real pain. So we basically have to put everything in inches. So as long as the forces are consistent, pounds with pounds, kips with kips, or with KSI, pounds with PSI, kips with KSI, and all the lengths are in inches, we won't have any unit problems. So let's find our deflection. Deflection is the force, which is, I'm going to go to kips here, 0.1 kips. The length is 72 inches, and that's cubed, all divided by 48. E, since I used kips in the top, I'm going to put KSI, 1700 KSI, and then I, my moment of inertia, 5.3594 inches to the fourth. Now I'm only going to show this part once to show that the units really do work out. As long as you've got them, got all the lengths in inches and the forces are consistent, it'll always work out this way. We have here KSI is a kip per square inch. Well, we've got inches to the fourth here and inches squared. So we've got an extra inches squared right there. The kips cancel out. And I've got inches cubed coming from the top. I've got inches squared in the bottom. So what I'll be left with as my final units will be inches. So instead of inches cubed, I'm just going to have inches. So my deflection will come out in inches. That's why the units have to be consistent. If they don't cancel out like that, you're going to get some weird unit for your distance, or for your deflection. It's not going to be inches, and will be likely high or low by a factor of 1,000. So let's calculate this out. We should expect reasonably small values. Here we've got 0.1 times 72. The 72 gets cubed. So 0.1, 72 cubed. So that gives us a pretty big number in the numerator. We're dividing that by 48, dividing that by 1,700, and then dividing that by 5.3594. So I'm getting 0.085 inches. So here I've rounded it down to thousandths of an inch. So 85 thousandths of an inch. That's not too bad. Now, if that was too much for us, well, we could decrease the span a little bit. That would give us a bit of a less deflection. We could increase the moment of inertia. Maybe we go to 2x6 instead. So this was for a 2x4. For a 2x6, all that changes is the moment of inertia. We have 0.1 kips. We have 72 inches, all cubed, 48, 1,700. And from our previous example here, 20.797 inches to the fourth. Well, if we go and calculate that out without showing the units calculate out, because we trust them now, 0.1, 72 cubed, divide by 48, divide by 1,700, and divide by 20.797. So there we definitely get less deflection, 0.021 or 22, down to the thousandth of an inch. So 22 thousandths of an inch. Now, typical codes, they specify the allowable max deflection, typically by the length divided by some factor. For example, you could say that the maximum allowed deflection is the length divided by 120. That's a reasonably common number. So for a 6-foot span, 72-inch span, we might be allowed a deflection of 0.6 inches. That's 5/8 of an inch, roughly. So that's a lot. Depends on what the code is and what purpose that particular beam is serving. It'll tell you they'll tell you in the code what the allowable deflection is, and you can figure out, well, am I above or below that? So that's the situation for the simply supported beam. Let's take a look at the cantilevered beam. So the cantilevered beam, the picture looks like this. We've got one end stuck. We've got one end set in concrete while the load is applied at the other end. Now, this is a more stressful situation because now the load is pretty far away from the support. There's a lot more material between the load and the support so that there's more to bend and more to change shape. So we should expect the deflections here to be bigger, even with the same materials, same numbers. So E would be our modulus for the material. Moment of inertia is going to resist bending. If the length is longer, we get more deflection. If the force is bigger, we get more deflection. So the equation is going to look pretty similar. There's going to be only one slight difference. Here we've got FL cubed, same as we had in the previous problem. We've got E and I in the bottom, same as the previous setup. But now the number is 3 instead of 48. So instead of dividing by 48, we're dividing by 3. That essentially means that everything else being equal, the cantilevered beam will have 16 times more deflection than the simply supported beam. So that means if lower deflection is needed, we need to go to stiffer materials, or we need to go to shorter lengths, or we need to go to less force, or we need to go to a moment of inertia that's bigger. So let's see if that works out here in our examples. So we'll take a simply supported beam or a cantilevered beam, and we'll make it 6 feet long. And we'll put 100 pounds on the end of it. And we'll see how much the maximum deflection is. Well, the deflection is FL cubed over 3 EI. So let's do it for the 2x4 case. For the 2x4 case, we're making this out of southern pine, so 1700 KSI. The moment of inertia for the 2x4 was 5.3594. So the deflection is FL cubed over 3EI. We've got 100 pounds or 0.1 kips. Got to keep the force and the modulus consistent. The L is not 6 feet, but 72 inches. And that's cubed divided by 3 times 1700 KSI times 5.3594 inches to the fourth. So let's see how much deflection we get. 0.1 times 72 inches cubed divided by 3 divided by 1700 and divided by 5.3594. So there, this is predicting a 1.366 inch deflection. So it's going to deflect a little bit more than 1 3/8 of an inch. And that's a good bit. That's maybe too much. We'd have to check the appropriate code. If we do the same thing for a 2x6, the only thing that was different for the 2x6 was the moment of inertia was bigger. So we have 0.1 kips 72 inches cubed over 3, 1700 KSI, and 20.794 inches to the fourth. So a little bit stiffer area because we've got a bigger moment of inertia. We've got 0.1, 72 cubed divided by 3, divided by 1700, and divided by 20.797, excuse me. 797. There we get 0.352. 52, there we go. 0.352 inches. So a little bit off from 3/8 of an inch. So that's a significantly smaller deflection. So just going to a higher modulus or higher moment of inertia material reduces the deflection. If that wasn't enough reduction in deflection, we want this to be stiffer. We could either go to even more moment of inertia, maybe replacing it with an I-beam that might have 100 inches to the fourth as its moment. Maybe we could go to a material with a larger stiffness, with a larger modulus. 1700 KSI is kind of low. That's wood. Most metals we were seeing were up in the tens of thousands of KSI for the modulus. 35,000 KSI, for example, for typical aluminum alloys. So the modulus could be a lot stiffer by a factor of 10 if we went to a material, 10 to 20 for a metal, if we went to a metal. So much stiffer there. But that's the basic idea behind deflection and bending of beams. And those are the only two cases that we're going to work with. So, and you have on homework 10, there are some examples to work through on that. And there are some practice ones also on the practice exam, because this is game for next week's exam. So next time, Monday night, we'll be doing a review session for exam 3. It's essentially student driven. So if you have questions off of the practice exam or off the homework or anything like that, bring them in on Monday night. I'll be glad to go over them live. If you don't have any questions, or if no one really shows up with questions, I'll go through the old exam and kind of point out some tips and tricks like I did for exam 2, and then end the session there. We also have quiz 7, our final quiz on homework 9. So that involves working with some stress and strain. All right, well, have a good evening, have a good weekend, and I will see you Monday night.